Hello everyone, welcome back to Exploring Quantum Physics. I'm Charles Clark. We're now going to start to apply some of the greatest tools that mathematicians have ever developed, the special functions, and apply them to solving problems of quantum mechanics of simple systems. Now, special functions, there are many good sources of information on special functions available, but it's not good to have a common reference so that everyone in this course will be using the same one. So we're using this, the Digital Library of Mathematical Functions from my employer, the National Institute of Standards and Technology. It's freely available worldwide, and it contains information on all the functions that we'll be using in this course and many more, and well, there are many other things to be said about it. But when I make a reference to something like the Airy function, which will be done later in this part, then what I mean are the specific representations that are provided there, which they're very much standard, the same that you'll find in Wikipedia, but I encourage you to look at this anyway. Several other resources for you. A short crash course on mathematics. That's something that's certainly worth looking at because it does provide constructed by Zach Raines and his collaborators, and it gives you a pretty good idea of the level of mathematical treatment that's done in this course. Another one-page guide to the known solutions of the Schrodinger equation in terms of special functions. And what else? A sample of a program written in spreadsheet form for solving the Schrodinger equation by numerical integration. So that's something I won't be using that in this part, but it's something worth looking at. There's a discussion there, and it'll give you some simple guidance as to how to numerically integrate the Schrodinger equation in cases when you're dealing with a complex problem for which there is no known solution. So, who was the first person to use this approach, solving the Schrodinger equation using special functions? No prizes for getting this right. It was, in fact, Schrodinger. And you might say that his first work, first papers on the wave equation were influential, well, for several reasons. But one lasting development was that it cast the Schrodinger equation of quantum mechanics into a form that had been well understood in classical mechanics, and that was to reduce the Schrodinger equation, a differential equation that had solutions in terms of functions that were known at the time. So what Schrodinger did, of course, his work, the importance of his work stands on its own. He explained the spectrum of the hydrogen atom, calculated the shifts of spectral lines, he invented perturbation theory, all in this series of 4 remarkable papers. But certainly it's very important for the wider implementation of his ideas that he developed a framework that mapped onto well-developed problems of classical mathematical physics, and so we're following the same approach here. So in this part of the lecture, we're going to look at we're going to stick with one-dimensional examples, and we'll look at a constant potential, a linear potential, and I guess it'll be in the next part with this quadratic potential. But you might say that these are the 3 simplest possible potentials in terms of development as polynomials, and the solutions of the Schrodinger equation for these cases are the exponential function for the constant potential, the Airy function for the linear potential, so this is exponential Airy, and parabolic cylinder for the quadratic. Now the harmonic oscillator is a special case of that, but we're going to go through in this part we're going to go through these 2 cases and try to infer from them some general principles that are relevant both for the analytical and numerical solution of one-dimensional Schrodinger equations. Right, so let's start with the linear potential. We just take v of x to be a constant. And so here's the Schrodinger equation. Now, the point is, we want to find solutions for any value of the energy. We want to find a general solution valid for all energies, because then, with such solutions in hand, we can find the particular solutions that we need to satisfy boundary conditions. You'll see why this is important in a moment. But for example, if you just consider a case where the potential is constant over different regions, constant at different values in different regions, and you want to find a wave function, the solution to a wave equation that is valid, it'll be sufficient to have this information so that you can stitch the various pieces together. So the approach we take is to transform the Schrodinger equation up here into a standard type. In this case, the standard form that we seek is here, where rho is a scaled variable, dimensionless variable, and then the plus or minus sign has to do with whether energy positive or negative. We know that energies can be any number on the real line, so we need to account for both of those cases. Okay, so we just take that system, we transform, we find a dimensionless variable, rho is kx, k is the wave vector, and it's depending on whether the energy is greater than or less than the potential energy. The value of k is determined by that. And so there's two classes of solutions. So when E is greater than V0, we have two independent solutions. So, let me just say again, as a second-order differential equation, any second-order differential equation like this one has at least two independent solutions. There are many different ways to choose them, but here I've given you two independent solutions, sine of rho and the cosine of rho. We'll say a little bit more about the choice momentarily. And then in the region where E is less than V0, the two independent solutions can be chosen of this form, e to the rho and e to the minus rho. So any other solution that exists in this region is going to be a linear combination of these two functions. But that means the generic behavior is divergence, because if you just take a random choice of these two functions, then the resulting solution is going to diverge as rho goes to infinity. And in the exceptional case where you just choose this function, then it diverges going to, and rho goes to minus infinity. Now that can be, changed by another boundary condition, but you have to be aware that for this particular circumstance, the generic behavior is divergence. So that's when that means that you have difficult choices that have to be made. So I'll make 2 points about this in some sense trivial Schrodinger equation, which either has oscillatory or exponential solutions. And that is, if you have a general understanding of the solutions, then you could do a piecewise approximate solution to a real potential. If you have a real potential that has some arbitrary shape, you can approximate it on a piecewise basis, and then by knowing how to solve the equation regions of constant potential, you can sort of propagate solutions between different such regions. This is something that's used in modeling semiconductor heterostructures and so on, or the photonic band gap materials are well understood in terms of having techniques to propagate a wave function across a constant region, and then to stitch the transition matrix together to see what the net result is. So actually, why don't we just now apply that approach to the simplest possible problem of crossing an interface, and we're going to look at an example that you see every day. If you look through a window, you see a reflection of yourself. I mean, even if the glass is transparent, there is some reflection, and so it turns out that this is a phenomenon that's an example of this, the potential step function in quantum mechanics. So we have v of x as a function of x. This is air. This is glass. So the propagation of a light wave as it enters a window is the same, very similar mathematically to the problem of a particle moving in a potential. So the way that is framed is that we have light incident from a large distance on the negative axis. That wave function is a form of e to the ikx. Then there's a reflected component, which is of the type r, reflectance coefficient times e to the minus ikx, and then the transmitted coefficient here. Now, how do we determine the effect of glass on light? Let me refer you to an inline quiz. So when light goes into glass, it's the refractive index of glass is about 1.5. That means that its wavelength decreases, and so that means that the wave equation, the spatial part of the wave equation in the interior has this form, and so now it's very easy to determine the reflection coefficient. So what we have a wave function on two sides of an interface, the air and the glass. So we have to match the values of the wave function at the boundary. So for x equals 0, that's very easy. It's 1 plus r here. It's t here. So we have to have 1 plus r is equal to t. And then we match the derivatives. This is the equation of continuity that's required in quantum mechanics. So once again, it's easy to differentiate this side, and the answer is ik1 minus r, and this side is just ik and t. And so now what do we do? Well, we divide. We take this side and divide it by the other one. So you see, I'm just taking this divided by that, this divided by that, equals that divided by that. Get this simple equation for the reflectance coefficient. So you see the k, the wave vector, disappears, as does the transmission coefficient, and then it's easy to invert this equation to get this. So the r is equal to minus 0.5 over 2.5, which is 1/5. So the actual reflected intensity is r squared. Coefficient is 0.004, so it's 4%. This is about right. When you put light through a window, at normal instance, about 4% is reflected. So in the next part of this lecture, we're going to explore the next sequence, next in the sequence of complexity, the linear potential.